So Dennis, the 800-pound gorilla in the room in cosmology. Well, there's dark energy, but dark matter. That's something astronomers have been living with now for decades. Maybe you could just talk about how we came to be convinced that it exists.
Sure. It's a long history. Actually, the suggestion of dark matter dates back not quite 80, 90 years, but it sort of sat there for a while without being seriously considered till the 70s. And in the 70s, the key development was that the spectrographs got sufficiently sensitive that one could trace the rotation of individual galaxies out to large radii. And that's important because the discrepancy between the expected rotation, given the amount of luminous material that you see, and what you actually observe becomes more and more noticeable as you go farther out in radius.
Mm-hmm.
And so these sensitive spectrographs allowed us to measure the rotation of galaxies out to very large radii, and the the conclusion that we couldn't explain the rotation given the amount of stars that we see in the galaxy became more evident.
And this was, of course, around the time CCDs were maturing and coming of age. So this was sort of driven by technology in part.
That's right. It was, in fact, it was the sort of the Redicon tubes. But yeah, it was definitely technology driven, as a lot of astronomy is.
Mm-hmm. Now, this simple inference to draw from a flat rotation curve was pretty uncomfortable. So I presume there was a little bit of denial, or people didn't want to actually believe the data said what it said, or they doubted the messenger. Or
yeah, I think you see the same thing actually in dark energy, that a theoretical argument is built that makes people more comfortable accepting the observational evidence.
Mm-hmm.
Because the observational evidence for something wrong with cosmology was there in comparing the ages of globular clusters to
Mm-hmm.
the implied age of the universe. And in galaxies, that became, the need for dark matter became strong when people looked at sort of other concerns. For example, Oestreicher and Peebles presented various arguments for for the presence of dark matter, the suppression of bars in galaxies, for example,
Mm-hmm.
and on cosmological grounds as well, that the matter density of the universe had to be larger, which naturally inferred that the individual galaxies had to have more mass than we
Mm-hmm.
expected. And so I think that sort of that theoretical prejudice, in a sense, laid the groundwork for acceptance of the observational evidence for rotation curves. Because in fact, if you, again, as I said, there had been evidence for dark matter for decades before this.
Mm-hmm.
And some of it actually very good. There's a very nice argument based on dynamics of galaxies in the local group. The fact that M31, the Andromeda galaxy, is falling toward us means that something has turned it back from the natural Hubble expansion
Mm-hmm.
and is bringing it back toward us. And a very simple dynamical argument for how much mass is needed to do that implies that the local group has a total mass of close to 10 to the 13 solar masses, which is much larger than what you see in stars.
Who was this? Peebles, or who did
No, this is Kahn and Vulture.
Okay.
And that's from the 50s.
Wow.
And it's very hard to get out from that argument. And in fact, that number is in perfect agreement with modern estimates for the mass of the local group.
Interesting. And then, of course, there's the Zwicky and Coma. I mean, that
Right.
there's a problem there with the messenger. I guess people didn't like Zwicky. So.
That's right, and that paper was sort of buried in a German journal. So,
Mhm.
in fact, even though everyone cites it, I doubt very few people have actually read it.
Right.
And then there was a follow-up paper a year or two later by Smith, doing the same analysis in Virgo and getting a consistent result. And even before that, there was a estimate of the rotation curve of M31 that actually shows that M31 has dark matter.
Mm-hmm. And what about the Milky Way? I mean, we started to map out Milky Way rotation when radio astronomy matured, and there were measurements of stellar motions in the solar neighborhood. Was there any hints in the Milky Way?
There are some hints, although because we're constrained to fairly small radii, they're at the factor of 2 level,
Mm-hmm.
which never really convinces astronomers. But there's an argument for looking at stars in the position of the sun, but looking sort of out of the plane of the Milky Way, and measuring the velocity dispersions of those stars relative to the amount of mass we think is in the galactic disk. This is an old argument by Oort. and you can measure the mass density of the galactic disk at the location of the sun,
Mm-hmm.
and he got a value that's about twice as large as what we see.
Right.
But again, factors of 2 are easy to argue away.
Yeah. Now you've used small satellites of large galaxies as probes. So sort of to say how that works as a method.
Yeah, so it's the same, in general, it's the same idea as the rotation curve. The farther you go out, the more discrepant you expect the implied dynamics to be from what you would infer from what you see. And the idea there is that most galaxies, including the Milky Way, have satellite galaxies that orbit them, and they tend to be at much larger radii than the size of the disk of a galaxy. For example, in our galaxy, the Magellan Clouds are the most obvious satellites. They're at sort of 50 and 60 kiloparsecs, so that's maybe a factor of 2 to 3 larger than the largest radii we can probe in the disk of our galaxy. But there are satellites that go out to several hundred kiloparsecs, so you can probe the dynamics of the system out to several hundred kiloparsecs. And the idea there is you measure the velocity. Unfortunately, you only have their radial velocity, so you only know whether they're coming toward or away from us, but you don't know their full three-dimensional velocity. But even so, statistically, if you have enough systems and you assume that they're not all aimed at you or aimed away, on average you can do some statistical estimate of the typical velocity of a satellite in a halo of a galaxy. And that from that you can then calculate the mass required to give it that much velocity and infer what the total mass of a galaxy is.
And I guess, and for more distant galaxies, you can, where you may only have a handful of satellites, you can just sort of stack and get better statistics.
Right. So in fact, for my thesis, we could only find on average one satellite per principal galaxy. And so, yeah, we had to put together a sample of 100 galaxies or so to get that measurement. Since then, larger samples have come around. Sloan and other surveys have provided larger samples, but the answers haven't really changed. And other techniques have been developed to measure the mass of galaxies, in particular gravitational lensing. And so with weak gravitational lensing, you can see the effect of a dark matter halo on the images of background sources. And again, you get sort of the same answer.
So now that so many galaxies have been studied, the early late types and so on, large, small mass galaxies, what are the sort of systematics of dark matter relative to the galaxy population?
Yeah, so that is a very interesting question. It's been very hard to pin down. So we now know that the halos do trace roughly the stellar mass of a galaxy. So if you do see a galaxy with a lower stellar mass, it tends to live in a lower total mass halo. But the amount of scatter around that relationship, how much that can vary, is not well quantified.
And that's a factor of 6 typically, right? Is it? Or dark matter to normal baryonic matter?
Well, so that depends very much on, so if you take the cosmological value and you assume that, then that's about right.
But we don't see all the baryons.
We don't see all the baryons, and particularly in small galaxies, a lot of people hypothesize that a lot of the baryons have been expelled due to violent stellar explosions or feedback from a black hole. So actually pinning down the baryon to dark matter ratio in galaxies, a total complete census of the baryons in a dark matter halo, is one of the things I'm working on.
So there's a kind of a complex evolutionary story as well, and the interplay between normal and dark matter. And that's taken a lot of work to pin down.
That's right. So that's very hard. So there are sort of two questions. One is this baryon census, and then the second one is how the baryons settle into the dark matter halo, because we know the baryons do not track the dark matter. They're much more concentrated, and so if, again, that's the reason why it was hard initially to see dark matter, because where we can observe where the baryons dominate the total mass. But understanding exactly how they do that and how they do it seems to be very well coordinated from galaxy to galaxy. There's actually the process is chaotic. These things come together in big lumps and crash together and all that. But then the properties of the galaxies that inhabit the halos are actually very well coordinated. Or you wouldn't see the relationships that we see between luminosity, velocity of a galaxy, its surface density, and so forth.
And what's the best way to describe this sort of spatial distribution of dark matter in the galaxies? It's presumably, I mean, it interacts with itself, so it's concentrated. But what is the shape of the dark matter
Yeah. So
profile?
from numerical simulations, because it's hard to measure, and I'll get to that in a second. But from numerical simulations, the shapes of the halos in radial profile, so how concentrated the dark matter is, follow a very simple description for all galaxies, from small to large, even for larger things like galaxy clusters. The dark matter seems to follow a very nice law where it's sort of steep in the middle, and it sort of comes to sort of a distribution that implies that there's just twice as much mass if you go twice as far out. But then there's an edge where it starts dropping off more rapidly again at the outskirts. And that profile is named after its sort of discoverers, and it's very well established that that's roughly what galaxies follow. However, the question then is, how do the baryons, that was a simulation of dark matter only, so then the question is, how do the baryons affect it? As the baryons collapse into this halo, they will help drag in the dark matter as well.
Mm-hmm.
If baryons are expelled, then they may help push out and sort of flatten the central profile of the dark matter halo as well.
Mm-hmm.
So there are still open questions on how these profiles are in reality. And so measuring it depends critically, though, on understanding how many baryons are there, because you measure a total mass of a system. You have to subtract off the stars and gas to get what the dark matter looks like. And understanding exactly how many baryons are there from the light you see is actually quite tricky.
Mm-hmm. So you talked about baryons having a complex history and sometimes being ejected from galaxies. Are there pure dark matter halos out there?
There have been claims, none of them terribly well substantiated, for large dark matter halos. We think that most galaxies, the simulations of the flavor of dark matter that most people think is correct, imply that there are tiny, tiny halos, much smaller than the current galaxies we see, inhabiting the large halo of a galaxy. Mm-hmm. So there should be lumps of dark matter within the halos of galaxies. And that people have tried to see, since those halos wouldn't actually have any baryons in them, they're hard to track down. But the gravitational lensing effect of those has been put forward as one way of trying to see that, and people have actually tried to detect that in terms of gravitational lensing of quasars and things like that.
Right. So maybe we should back off, and since we're talking about lumps of dark matter within halos of dark matter, maybe we should talk about hierarchical structure form. How did dark matter get that way? How did the universe get the way it is?
Sure. So it from early times, from something called inflation, when the universe is in a very hot early phase and expanding very rapidly, there are imprinted on it very tiny fluctuations of matter, and those grow gravitationally over time. We see the fingerprint of those is seen in the cosmic microwave background. If you take those fluctuations, which are a part in 100,000, so that is, if you had a temperature measurement of the microwave background, one part of the universe is different by a part in 100,000 than another. So they're very, very tiny differences. But over time, gravity has a way of increasing those, because if there's any place in the universe that has a little bit more mass, it attracts more mass. And those grow over time to the current day, to the halos that we have today. Mm-hmm. That growth has been modeled very well numerically in computer simulations to match very well what we see today. So, in fact, that part of the story is well understood if dark matter is exactly what we suspect it is.
And of course, a key part of this from the very early phases, because you were talking about lumps of dark matter within a big lump of a halo of dark matter, and then we have clusters, is how the fluctuation, how the non-uniformity of dark matter is distributed on different scales. What do we know about that?
Yeah, so these fluctuations start in tiny lumps, dense lumps. Those then fall into other lumps, and that distribution in the universe it develops this very sort of web-like filamentary pattern, and so the halos of dark matter sort of fall towards each other along walls and filaments of dark matter that's there growing in time. In sort of the nexus of these filaments, you see large clusters of galaxies which have a lot of total mass and a lot of dark matter. Along the walls and filaments, you see galaxies, and then in the regions between the walls, which we call voids, you tend to have a small number of galaxies developed there.
Mm-hmm. And you mentioned flavor of dark matter, so just to talk a little bit about what the possible flavors are and how we could decide between them.
Right. So in astronomy we sort of deal with dark matter very generically. We don't really attribute it many physical properties, but the one we do is sort of what we call the temperature, and it depends on when the dark matter actually sort of becomes independent of the rest of the universe. And the common type of dark matter that most simulations have dealt with is something called cold dark matter, and it's cold because you can think of it as a fluid that doesn't have large internal velocities, which means that any little clump that forms will stay a little clump. The dark matter in that clump does not fly out of that clump. And so it means in that flavor of dark matter you get very tight, small nuggets of dark matter growing. Something called warm dark matter, there the particles have a larger streaming motion, that is, they have large velocities relative to each other. So even if there is a lump that develops, the stuff just flies out of it. And so you don't get these very tight, coherent nuggets. What that means for a galaxy is that these nuggets will fall to the center of a galaxy if they exist. And so in a cold dark matter model, you expect a lot of dark matter at the very centers of galaxies. The profiles will be very peaky towards the center, whereas in a warm dark matter model, you expect that material to not fall as much towards the center, and you'll have a much shallower profile in the center.
And you're sort of alluding to something that's very important in cosmology in general. In a state of still fairly high ignorance about the fundamental nature of dark matter, we use simulations in a very interesting way. I mean, they sort of guide us a little bit. Just talk a little bit about how people use and are informed by simulations.
Sure. So, the development, again, another technological development, the development of high-power computing has really enabled this to go forward. You start with some concept of what you think the initial universe looked like, at least at some very early time. You get to that point with the analytic knowledge that we have about the universe up to a redshift of about 1,000. At that point, you start a simulation where you distribute the mass according to that understanding you have, and from then on, you just let gravity do the work in that simulation. And that's, of course, where the technical innovation has been into these simulations, is how you actually do that, because even with the increased computational power, you can't just put each particle in there and then calculate the force that every particle has on every other particle all the time. It's just too computationally expensive. So a lot of techniques have developed to approximate that, but with that now we can simulate the universe with hundreds of millions of particles. And so, but it's just gravity doing the work forward. So the physics itself is actually well understood in a dark matter only simulation, because dark matter doesn't interact in any other way in these simulations other than through gravity. So that simulation is fairly straightforward.
And that alone presumably is enough to say that the universe we live in looks more like a cold dark matter universe than a warm dark matter universe.
That's right. So the initial big success of this approach was that people had speculated perhaps that the neutrino was the dark matter. We knew that neutrinos existed, so that was an obvious candidate for dark matter. And so you could put that into the models, and it turned out that model, which is called a hot dark matter model, looks nothing like the distribution that we see today. So it's much smoother because it's very hot dark matter, so it doesn't form a lot of structure. And so, that, in a sense, the first experiment was a failure, but it was a success that it taught us something very important about the universe, that neutrinos aren't the dark matter.
And just to tie that to more recent developments in particle physics, I mean, neutrinos were thought to be massless for a while, and now we know they oscillate, though we don't know their masses. Do they have any role to play in structure formation, given what we understand about neutrinos?
So, They do at a very small level, so not in the sense of impacting the shapes of galaxies. They're not sufficient, sufficient fraction of the dark matter to do that. But now when we look at the microwave background, the measurements are sufficiently precise that you can actually see the effects of neutrinos in the various, in the power spectrum of the microwave background. So you can say something about neutrinos. They do have a role to play, but they wouldn't affect the halos of galaxies.
Does it actually go in the reverse direction? Or do we learn enough from microwave background about neutrinos to inform
Yes.
the physicists trying to look at their properties
Yes.
directly?
So indeed, if you wondered about whether there are other species of neutrinos that we haven't quite yet found in the lab, the microwave background tells you about
Tells
that.
you no.
No,
Tells you
that's
we're
right.
not missing anything.
That's right.
Okay. So I think you were going to get to what happens when you try and go beyond just dark matter only. It gets a bit messier.
Right. So the current challenge in simulations is to do a good job of getting the baryonic physics, how the baryons settle into these halos, how they form stars, how those stars then affect subsequent infall of material and so forth. And yes, the problem there is that the physics gets much more complicated, not only technically in the sense that it becomes harder to follow it because you now have all this other physics that you're trying to include in the same simulation, so computationally much more expensive. But a lot of the physics we don't understand, so we don't understand how stars form. We don't have a model that really explains how star formation works. So even if we had infinite computing power, right now we couldn't really do star formation very well. So a lot of the important physics gets put in there by sort of a recipe, and that's unfortunate, but it does test the recipes at least. So if the models, if the simulations don't produce what we see, we know the recipe is wrong.
Right.
So on both the technical grounds and the sort of basic science grounds, those simulations are quite challenging.
Now you mentioned another innovation that was a function of technology more or less that's transformed our ability to probe dark matter, lensing, and you just talk in general terms about how lensing tells us about dark matter in different ways.
Right. So as light travels through space, it doesn't actually follow a straight line. It gets bent around because the space is curved. And what curves the space is mass. So a large mass between you and the object you're observing can actually cause the light from that object to sort of bend around. It can do a few things. In a very dramatic case, it can actually make it appear that there are multiple images of the object. In more subtle cases, it just distorts the shape of the object. And so, if you just see, for example, that there's an object and it has several other images of the object are nearby, you can already right there infer how much mass is needed to give you that image splitting. For the what's called weak lensing, where you just get a slight distortion of the image, you need to average over millions of galaxies effectively to beat down that statistical noise, because you don't really know what each galaxy looks like. So you have to sort of statistically say that the galaxies are distorted from what we expect to be a random distribution. But then you can see the effects of the mass on very large scales. And you can trace it from everything from galaxy halo sizes up through clusters and walls and filaments and all that.
And of course, it's an interesting sort of coincidence of the physics that these deflection angles for a typical galaxy are just sort of on the edge of what you can do with sort of poor ground-based conditions. So, I mean, Hubble was a transformative capability for some of this work.
That's right. So, particularly lensing actually provides you many opportunities, and one of them is that it stretches the image of the background galaxy. So if you care about using lensing to see distant galaxies, yes, Hubble is fantastic because you now have a high-resolution image of that distant galaxy. For statistical weak lensing measurements, you still do better from the ground just because of the large survey volume you have. So LSST eventually will be the weak lensing machine. And seeing better than a few tenths of an arc second doesn't really gain you much.
I see. Okay. And what, just since you mentioned LSST, and it's going to be a weak lensing machine amongst other machines, what, given where we are now with dark matter, what are the big questions that it might answer or address.
So it will basically be able to tell us how the mass fluctuations have grown over time. It'll be a direct measurement of how those mass fluctuations have grown over time. So we have the models, but this will be a measurement, and that will be sufficiently precise measurement that it'll tell us about dark energy. It'll tell us if the basic cosmological model is right.
I suppose we should give a little attention to, other possibilities. We were talking about lensing as a prediction of general relativity, and I guess right through the early history of dark matter, people realized that if you tweak gravity, Newtonian gravity, not that much actually, you could sort of explain it away. What's the sort of history of approaching it that way, or is that still a viable thing to even consider?
I think it's still viable. So the problem in general has been that every deviation you saw was centered on a lump of baryons. So you looked at a galaxy, and as you went farther and farther away from the galaxy, you saw a larger deviation from your expectations. So it could be that there's a lot of dark matter out there, or it could be that gravity, as you go into this weak regime, is not what you think it is. So in fact, one of the most popular versions of alternate gravity posits that there's a floor to the acceleration, that it doesn't get infinitely small, that when it reaches some very low level, it flattens out. And that has a very, it fits galaxy rotation curves extremely well. It does a very good job of fitting galaxy rotation curves. It's not a physical motivated theory, so it doesn't explain other things on different scales well, but again, since it's not physically motivated, it's hard to say that value isn't different on different scales and things like that.
Well, do we have any other, independent reasons from other arguments to be suspicious of the gravity law, or I mean, apart from the fact that it's hard to truly test it on beyond solar system scales?
Well, there's certainly, there's a history where we've seen, that our understanding of gravity was not correct. So, Newton's gravity does not explain everything we see, and that's why Einstein's general relativity actually does a better job of explaining a lot of phenomena that have come along. So it's not impossible that general relativity isn't quite right and that there's some modification necessary. And so I think on that sort of philosophical sense, people still are willing to sort of think about alternatives. But there's certainly nothing, there's no proof positive of something that dark matter doesn't address, that only an alternate gravity theory would address. So at best, these alternate theories do as good a job as dark matter, and nothing else. So that's sort of where we're at, and now there's actually good evidence that, in fact, so as I was saying, the problem was usually that there was always a lump of baryons around this thing that we thought was dark matter. And you had asked earlier, do we know of dark matter only lumps?
Right.
And of course, a dark matter only lump would be an excellent test case against an alternate gravity theory, because there wouldn't be anything there in a regular model. And so there's one example of a very nice example where two clusters have collided. Two clusters of galaxies have collided. And in a cluster of galaxies, the baryons are mostly in a hot gas, not in the galaxies. And when that hot gas collides with hot gas in another cluster, it sticks. Whereas the galaxies and the dark matter fly through each other. So this is a case now where the universe has arranged to sort of separate the dark matter from the baryons. And so there you can look, and using weak lensing to see where is the mass. Is the mass still with the baryons, suggesting that we just aren't understanding things properly? Or is the mass now in some other place where the dark matter is? And the weak lensing shows that the mass is off of the baryons. It has flown through. So that's a very good sign that there is dark matter. It doesn't necessarily say that we understand gravity perfectly, but we would at least need some dark matter.
So this is a lot of progress in 40 years, from just complete mystery to a lot of descriptive capabilities on dark matter. But let's let's finish with what it is and what it isn't. I mean, we've made some progress at least in eliminating things. People might say, well, it could be black holes, it could be Jupiters, it could be dust particles, and there's a lot of things we know it isn't. And so maybe talk about that and what we think it really is.
Right. So so without a full accounting of baryons and knowing exactly how many baryons we expect and all that, there was always the possibility that it was normal stuff just in a very dark form that we can see. And so that ranged from black holes to very cold gas to Jupiters to cosmic bricks, whatever stuff out there that just was in the right sort of temperature that we just wouldn't see it very well. In a sense, so there have been a lot of experiments that helped rule out various parts of those. For example, microlensing experiments towards the Magellanic Clouds ruled out things of the size of Jupiter. And that's because these Jupiters, even though you wouldn't see them, would lens the background stars, and so you'd see that. And that was not seen, and so you could rule out a large class of
Actually, a
objects
couple of decades ago.
That's right. And so there have been experiments like that have ruled out different classes, but I think in the end, the whole sort of cosmic baryon inventory and the measurement of the matter density of the universe just says it can't be, right? We know from Big Bang nucleosynthesis that there's a certain amount of baryons in the universe. We know now very well how much mass there is in the universe. The baryons are a small fraction of the total mass. So it's not, so the dark matter cannot be baryonic.
Right.
Now, beyond that, now there are many models for new particles, different kinds of particles that particle physicists dream up of. And there's an array of experiments out there attempting to identify signatures from different candidates.
And of course, astronomers have done the heavy lifting of characterizing dark matter for decades, but these are terrestrial experiments. These are down in mines and in labs and so on.
Yeah, that's right. In the ocean, in the Antarctic ice, they're all over. Different people have different expectations for what the dark matter might be, and so they set up experiments designed to find their candidate, what they think is the most likely candidate. So far, mostly null detections. There have been a claim or two, but those have been very controversial. I think the state of the art right now is limits on what it can be.
And what are we talking about? Because people know about the Higgs being discovered, which sort of ties a bow around the Standard Model, but the Standard Model is incomplete, right? So anything we're talking about is beyond the Standard Model, and what are the candidates the physicists are most excited about?
Well, so there's a range. I'd say the WIMPs, which are weakly interacting massive particles, which come from a supersymmetric type of model, are sort of what most physicists are looking for. So there are a range of experiments set up to try to detect those. In fact, even those have very strong assumptions for what the mass of the WIMP might be. And, it'd be great if that's what it is, but it could actually be much lower, and the inner cross-section might be much lower, even if there is a WIMP. It could elude the current experiments very easily.
So even though the physicists know the target they're aiming for, they know how much dark matter, the sort of density of dark matter in the universe, that doesn't mean that these experiments are so well defined they will succeed or fail.
That's right, because these models set up a family of alternate particles, and they decide that the dark matter would be the most massive, lowest energy state.
Right.
But there's a whole family, and it could be anywhere in that. Right. And in fact, there's no real reason to expect the dark sector to be as simple as a single particle when the sector we know about is very complicated.
Right.
And so dark matter may in fact end up being 1/3 this, 1/5 that, 1/7 this, and so again that would lower the likelihood of finding it in any of these phases.
And suppose one of these experiments was successful. Is that's sort of the physicist taking over? Are astronomers still going to have a game to play here for dark matter?
Yeah, there's still be quite a bit. Even interpreting the physics result would be very astronomy sensitive. So there are questions about how lumpy the dark matter. We'll just measure it in one place in the galaxy. So is that a fair then measurement of the density of dark matter everywhere? And you'd need to know that to understand if you've really found a dark matter or if you found a dark particle. You know, to some extent, neutrinos are the first dark matter particle found. They have mass. They're dark. So we've already solved the dark matter problem, but a very small part of the total mass.
Right.
Yeah.
So I guess my last question would just be to taking the big picture view of the subject. You know, cosmology, observational cosmology, seems to be a fairly mature field, and yet, you know, this is a pretty big component of the universe to be so unsure of. What's your sense of the maturity of the field?
Yeah, I oscillate wildly. I mean, I think the modeling and the structure modeling is truly beautiful. Starting from the microwave background, which is almost perfectly uniform, not quite, you can explain all of the structure over many orders of magnitude that we see today.
Mm-hmm.
So that's an incredible success. You know, we sort of know how the universe has evolved from redshift 1000 to now, in its dark matter properties. On the other hand, as you say, we don't really know what the dark matter is, so that's a whole unknown. And dark energy is even worse. So, so maybe it will be that we've just completely misunderstood gravity, and cosmology is all happens to fit this model very nicely, but in fact, it's the wrong model.
Right. Well, we're observers. That keeps it fun.
Yeah,
It keeps it interesting.
Absolutely.
Yeah. Okay, thanks a lot, Dennis.
All right, you're welcome.